January BSUG. You have Gunnar here today. He's going to do a little presentation on THERM and a demo for us as well. Before we get started with that, next month's BSUG will be the third Wednesday of February, and it's going to be energy and lighting impacts of algorithms. So we're going to look at blind controls and simulation. And that'll be done by Amir and Alan here from the lab. So if you can join us for that, that'd be great. And I'll send out some details on that. And that's all I have. I hope everyone got signed in. I'll pass around the sign-in sheet to make sure you're all on there. And feel free to grab more food or drink if you need it. And with that, I didn't print out all your bio. Gunnar was with us here at the lab for about 5 years and then has recently moved to Hummel Architects, where he's their, what's your title? Sustainability?
Building performance.
Building performance expert over there. So we're glad to have him back today and share a little about THERM with us. So that.
Thanks, Katie.
Also, if anyone in the room has questions, I'm going to try to get you this microphone so that as well. So raise your hand.
All right. Thanks for coming today. Well, first, has anybody used THERM before or played with it, maybe at least? A little bit, a little bit? Okay. So I think it'll be a good introduction. Maybe not. I've got some advanced stuff. I see a couple passive house people that probably know a thing or two about some of the other stuff. But so what I wanted to do is talk about the effect that thermal bridges have on building and energy performance, and discuss how it relates to code issues and look at, I'm using the IEC 2012 version of the code as a basis to talk about some of the performance parameters. Whenever we talk about thermal insulation, I think it's really important to talk about vapor diffusion and liquid and vapor management in the wall system as well. So we'll just talk about that a little bit so we don't miss it and have water issues when we start using plastics or increase insulation rates in certain places. I wanted to talk a little bit about the way that the code has us do prescriptive things, but it also allows us to do performance things. There's a lot of choices that we can make that don't have to follow the prescriptive requirements as long as we design the walls to perform to the minimum requirements. The more advanced piece of what we'll talk about is to do with linear thermal bridging. Linear thermal bridging is not covered or mandated in the code. But it's something that can affect the performance of the building quite a bit. So if you're looking for additional performance, you might want to start doing some calculations to understand how much you're losing out of the details. And then I was going to do, hopefully I'll have maybe 15 minutes just to play around with THERM. It sounded like most people hadn't really played with it before, so just looking at the interface. Free software from Lawrence Berkeley National Lab, so of course it's not that easy to use. But it is, there's some really expensive three-dimensional thermal modeling softwares that people use that it's like a bazooka for what we need to do. So simple 2D heat flow will solve most of our problems looking at architectural details. I also wanted to some of the materials from my past work experience from the lab. So the lab's done a lot of work in THERM. That's where I did most of it to start with. There's a lot of references to some of the work that Morse Nursefield has done. They've had a few ASHRAE research projects. BC Hydro sponsored a really good, Katie actually found it the other day, a guide to modeling thermal performance in walls. And then I used some references from the Passive House Academy as well. So thanks to all their graphics and things that I'm using today as well. So just in general, an envelope has to do a lot of work. We have to design it to hold the building up, keep the rainwater out, keep the groundwater out, keep the wind out. The things that we'll kind of focus on today a little bit more are to keep the water vapor out, keep soil gases out. It's important to let the water and water vapor out when it gets in, and keep the heat in during the summer, and to a lesser degree to keep the heat out during the summer, or excuse me, keep the heat in during the winter, and keep the noise out. Some of the other things, we have to meet NFPA requirements and all these other things as well. So on top of that, there's more things that we have to be worried about. But today, most of the focus is thermal control, and in that relationship, because thermal control and moisture and vapor control are so closely related, I'll talk about it a little bit. Overall, when we're talking about the integrated design effect, and there's a lot of things going on with the building's performance, but when we're looking at really fundamentally sizing heating systems for a building, we're looking at peak sizing conditions, and you can tell me this is wrong, but most of it's from the envelope losses, infiltration losses, and then and then a good chunk of it's from ventilation requirements to satisfy fresh air for people. If we can design 50% better envelope, our peak sizing conditions can be reduced quite a bit. And thermal bridging isn't going to do all of that, but it's part of the equation in doing that. So it's an important piece to try and get to these next step integrated envelope mechanical system solutions that we're trying to get to. Some work from Morris and Hirschfield studies from ASHRAE research projects that's doing a thorough job of modeling all the heat transfer through the details. Basically, 2 to 5% of the heat loss in the building can be due to different thermal bridging effects. So as we ratchet down on our insulation requirements, kind of the leftover, the low-hanging fruit is now in a lot of the detail areas. It's not quite as easy as just throwing more insulation into the wall. IECC 2012, or the CC 2012 here, I can't quite see it, but so this was to kind of talk about how the code helps us do things. There's a simple way with the prescriptive. We can go and see if we have a mass wall, then we know that in climate zone 5, we need to provide 11.4 CI, and the continuous insulation definition of CI is that doesn't have, you're not putting studs between that and the wall. It has to be a continuous layer of insulation. The requirements for metal frame building allow for some cavity insulation, R13, but also still require at least R7.5 CI. That's usually done with some outboard insulated sheathing of some kind or another, and then using R13 for the batt insulation. Some of these other ones, so let's just keep looking at those two actually, for instance. And when you go to the other method, U value, you can use this as a performance way to do it. There's several ways to do it. If you have a uniform wall assembly, if it's continuous insulation, CMU, maybe something else on the inside, you can usually use a spreadsheet to figure that out if it's something that's unique or not already in some table. But if you have different stud layers, and it can be a little bit more difficult to figure out, and that's when I've used THERM, instead of using a spreadsheet to calculate the clear wall U value assembly. And one of the things to note, so that mass wall used to be, the requirement in the prescriptive is R11.4 CI, and that was the same as the 2009 code, but it used to be U.09, which was not quite as stringent. I think they figured out that if you're sneaky and you can use the software, you could use less insulation than they intended. So this is more in alignment with what, if you model it and it's closer to the prescriptive. But typically the prescriptive requirements have more insulation if you actually model the whole wall than you would need to meet the performative requirements. Does that make sense?
Is there a reference somewhere that has those?
I built my own, but if you just look up calculating U value, that you just a quick couple pieces of math, sometimes the hardest part is searching out the material properties. Engineeringtoolbox.com is a good place to look. And then when it gets kind of to some more tricky assemblies, because unless you're using THERM and you want to know what's the average U value of a CMU wall that's grouted every 32 inches with medium weight concrete, and that's, you know, there's a table for that, and the Concrete Masonry Association has studies that list that kind of stuff. So you don't necessarily have to go to THERM. You can sometimes find that stuff without going to the next level. So in reference to that, and I did circle our, you know, typical climates for Idaho, 5 and 6. Those are mostly what if we're doing projects in Idaho, those are the climate zones that we're dealing with. So this is to stop to talk about vapor barriers and vapor control in walls as well. So it's kind of interesting, actually, if you look at, this is out of the IBC, not the IECC, so I have to cross-reference a little bit, but if you look at this table 1405.3.1, and you look at the zones for the climate zone, when it says that your insulated sheathing R value is over R5 on a 2x4 or R7.5 on a 2x6 wall, and that's typically what we're going to see, right? So if we have a commercial building, we're doing 6-inch metal studs, and the prescriptive requirement right here, it tells us, hey, metal frame building, you got to use R7.5. If you follow the prescriptive requirements, then it's telling you not to use a class 3 vapor retarder, which I handed out some references on the PERM ratings of various, that's just basically the definition, so you can keep that as a reference. Doing is you can use level of vapor retarder instead of putting plastic in your wall. When you have a sheet of insulated sheathing there, it's another layer of plastic. So when people are typically used to putting a layer of 6 mil or 8 mil poly on the inside face, and now you've got 2 layers of plastic. So when you get moisture in there, then it's can't dry out, can't dry in. So this is that code allowance to say you can use, basically it's a low perm paint. It's still breathable, but it's not as much of a barrier as plastic on the inside face of the wall. So that's if you have insulated sheeting over these limits, and then you want to get rid of that plastic and use a class 2 vapor retarder.
But you can actually use a class 2 in our climate without exterior sheeting.
Yeah.
And so class 3 is what we use if you have exterior sheeting.
Right. Right. Yeah. Now, see, Scott, he'll correct me. He does more of this than I do. So just as a note, because I've seen a lot of details where it's common to see the plastic on both layers. I think probably, Skylar, you've seen that. People do it because they remember that that's what they used to have, and then they add insulated sheathing, and you get a sealed cavity of 2 layers of plastic, which is no good. So that just is just the definition of the, so the class 1 materials are 0.1 perm or less, so that's the plastic. And those are basically vapor impermeable, vapor barrier. When you say it on your plans, it says, if you say vapor barrier, that means less than 0.01 or 0.1 perms. Class 2 is up to 1 perm and greater than 0.1. Vapor retarder, so the difference between barrier and retarder when you're using that language, or vapor semi-impermeable. Class 3, 10 up to 10 from 1 to up to 10 perms, and in class 4 anything more than 10 perms. And so I have a list of some different materials just to kind of think about that. So if you're using polyisonuranate on the outside face of the building, you can see the dry cup rating, which is the ASTM test that's listed on the top of that reference sheet, which classifies the materials. Then that perm rating is really low. That's way less than 0.1. And so you can look at XPS rigid insulation. That's still 1, but if it's at 1 inch, if you're going over another over an inch, then it's going to be less than 1 perm dry cup method. So those would be basically classified as vapor barriers. Class 2 range between 0.1 and 1. And then fiberglass and cellulose, if you're putting those in your wall, you know that those are basically just vapor permeable, and air and water flow can move back and forth between those materials. And the other important, as far as vapor diffusion goes, to talk about those particular elements. If this is with a class 2 vapor retarding surface on the interior face of the wall, so you're going to slow down a lot of that vapor getting into the cavity that wants to make its way to the outside. This one, class 3, which is the more permeable of them, this wall basically breathes all the way from inside to out. And then this is the condition that we were talking about, or that I was just talking about before, where class 1 vapor barrier on the inside face, so you can't, water does not want to get out, but it'll make its way through this wall assembly and hit the outside face of the wall, the sheathing where it's cold, and it can condense there. And that, I guess the point that I wanted to make is that when you use those class 1 vapor barriers, we still have tons of different holes that we put in the walls all over the place for switches and electrical outlets and lights and everything else. And so unless all of those are perfectly sealed up to class 1 vapor barrier level, then you will have moisture migration into the wall cavity. And if you have a material that allows, such as fiberglass bats or some of the other cellulose materials or those kinds of things, you'll have moisture migration to that cold surface. And so it kind of makes more sense to use a little bit less, especially when you start using the exterior insulated sheathing, to use a higher class vapor barrier, vapor retarder. It's hard to get them all straight. This is just a good example from Joe Stiebert's book of not about actual diffusion through materials. So he's saying a full sheet of gypsum board with normal interior humidities and temperatures. If you can push about 1/3 quart of water through that actual solid material. But if you have a small 1-inch square hole, all the air transported through the hole equals about 30 quarts of water. So air movement in the assembly, basically those outlets, anything that's letting air flow around in the cavity, is where you'll get a lot of this moisture transport. And so in solving that problem, one of the things that we're starting to do, or getting those higher levels of insulated sheathing on the outside, creates a warm wall. So the back edge of the wall, it's not like this assembly where we just have sheathing on the outside and that condensing surface is really cold. We start having insulation on the outside, then we get a surface that's warmer than the condensing temperature, and we won't have that issue. I think people probably remember the drive-it incident that happened in, I think it was the 80s or 90s. There's an impermeable layer of foam that was really thin on the outside of the buildings. Water got to the outside face. It was cold enough to condense, sucked up all the water, but it couldn't dry out to the outside, so there was a lot of rot issues. That's basically what happened. Even with not enough foam on the outside, that needs to be the right level of insulation on the outside to make sure that inside surface is warm enough. And so basically what they're looking for is, over the time of the year, this is the traditional wall system, where you have that outside face where the blue line is right there. It's going to go through some temperature changes as the outside temperature changes. And what they're concerned about is when the outside conditions and the inside conditions, this is when the temperatures are too low and the inside humidity level is going to get against that condensing surface and potentially condense to liquid water. If you're using the exterior insulated sheathing system, the heat transfer is going to be, the temperature of the surface is going to be much higher because of the insulation that you have on the outside face of the wall. So that actual temperature profile of the inside of the insulation, or the inside of the OSB, that's able to stay above the condensing line for the most time of the year, depending on the interior conditions. And so it's important that the thickness of this material is important. If it's too thin, you get that drive it issue, especially if it's impermeable and it's not thick enough, you get condensing on that surface. So this needs to be minimum, and that's basically what the code's trying to do with their minimum values for the CI on the outside. But if you're going to do design to the U value, and you're going to use, you think, well, I talk about the vapor controls. It's important to remember when you're trying to design wall systems. Another example, and this one illustrates why they, you know, some of those walls you see R13, you're in a 6-inch cavity. It's like, well, why not put more cavity fiberglass bats in the system? Well, one of the things that's going to do is it's going to slow down the heat getting to that exterior layer of insulation. So in these two examples, you can see this is an example with, say, this is just an example, R10 insulation. The outdoor temperature is down towards 0, like the design temperature. And the profile of the temperature in the wall, most of all of the insulation is right here, so most of the temperature gradient happens right here. So the inside face of this wall is 60 degrees. No problem. You're not going to get condensation on the inside of that wall. You're only going to be at R10, but no condensation problems because the inside is warming up that surface readily. If you throw R19 in this wall, a lot of the insulation is going to, a lot of the heat resistance in that cavity. So by the time the heat gets to this face of the wall, there's not much more to go. So now your temperature is, you know, pretty far down. That could be a problem. But what they're showing here is when you jump back up to R12 or R13 bats in this wall, then there's more heat getting to the surface before it lets this thing do a lot of the work. So that's kind of why they have the intent behind listing the R7.5 for climate zone 5 and then R13 rather than jumping it up. So if you're trying to add cavity insulation, 1, it doesn't do that much after a certain point. But 2, it also does retard heat flow to a surface where you might need a little bit of extra heat. Does that all make sense? It's really, I have to read through it like every time I'm looking at different materials. So on to the thermal bridging piece, I wanted to reference, and this is, you don't have to remember anything from today because there's a lot of the stuff that you might need on your typical practice. If you just Google the ASHRAE Research Project 1365, they have a ton of different solutions and wall systems with the actual, with showing the nominal and actual performance values of those different wall systems and their U values. Because there's a big difference between, say, this system where you've got your steel studs and you're using a vertical Z-girt to attach siding on the outside of the insulation, or you're doing horizontals, or maybe you're doing intermittent clips. And those all have a pretty significant difference between the results. So this is some of the information that Morrison Hirschfield published in that RP. And so what they'll run you through is all the different kinds of insulation values for different prescriptive amount. It's a R19 or whatever, but that's not really what it is. So here's an example, and this is just for steel stud walls. I have a whole bunch of other ones. So down on the bottom, you can see the nominal R value, and then you can see over here the actual performative R value of the actual wall assembly, Clearfield. So a lot of what they use it for is to help with the rating system and the classification for the windows, NFRC ratings that we need to get on our windows nowadays. So they'll look at the frames and be able to thermally model the frames, do that. So that's a little bit more complex than we need, just maybe for our architectural piece. But you can also just model architectural walls, wall to slab, wall to patio, cantilevers, parapets, clear wall assemblies if you're just trying to figure out, well, I've got a kind of challenging condition. Maybe it's a retrofit, and you need to get, you want to try and really do it like you normally would, and you want to do spacers with steel studs off of the masonry wall and put spray foam in it. This can help you try and see if you're meeting your performance targets. So we've done a few. I mean, these are really just really standard walls, but doing different stud spacings and different information. So this is just this is basically just a steel stud wall with insulation, sheathing, rigid insulation. I think this is a code wall. And you can see, and this we just built this in THERM, you can see all the heat transfers happening at the steel. But basically the program will spit out, so you can see the U value. The U value performance of this is actually better than those prescriptive requirements, which is typical. Allowing for, you know, if you had to go to a 12-inch, or they're allowing for stud packs for windows or doors or things like that, you're going to get more thermal bridging. So they're kind of over-designing it on the code requirements for the prescriptive, knowing that the U value in the clear wall is going to be a little bit better. So this is one of the things that we've got lists of different wall assemblies. This one is the regular code assembly. But you can do, this is an example, this is one that we did at the lab, where we were just looking at just the effect of moving something from having full contact between concrete masonry unit and concrete interior wall, and also a stud wall system. So these are in full contact with the stud wall, putting studs straight up against the CMU wall, having a thermal bridge from inside to outside. These are ungrouted CMU walls. So they meet the code values for the mass wall. The U value was too high at 0.1. And in this particular case, which was a couple code cycles ago, if you just introduce an air gap to the clear assembly, you're able to get a little bit better performance out of it. And that's just basically debridging. You know, you could put, this is just an example of how it works, but you could insulate this cavity as well and obviously drive the insulation values up further. But just to note the difference between having it touching and not touching, basically thermal bridging through that assembly. Either one of these stud systems worked. This one was plenty enough to meet the code minimum, and then this one only had a little bit better performance than that one did. So of using it. So the kind of the next thing, basically the clear wall assembly. This is basically what you get if you're doing your spreadsheet system, and you're just putting in each layer of materials, 5/8" sheeting, 6-inch stud cavity with fiberglass bats, gyp wall. You can even add your air boundary layers on the inside and outside, and you just get a continuous linear a number that's based on the Clearfield. So if you start introducing different studs and different things into the wall, what you really have is something that will perform quite differently, and that's what that Morrison-Hirschfield study did. Is it looked at the three-dimensional systems. So that's the tough part. They did three-dimensional modeling to get the interaction of vertical and horizontal girts, because we can only in THERM draw sections. So we have a simple stud wall. We can figure that out. When we start adding vertical and horizontal girts, then it gets tough, and we can't quite do it from our perspective. We have to go look at one of their research projects and figure it out. But the other concept that I wanted to, everybody's pretty familiar probably with R value and U value. They're the inverse of each other. One measures the time that it takes for BT to skip the outside wall. One measures the amount of energy transferred based on the time foot squared, area foot squared, and degree Fahrenheit. One of the other things that beyond the clear wall assembly that we have to deal with, and that's what we were talking about basically thermal bridges, is what's known as the psi value, which is a linear measurement, and this might be where you have your regular wall assembly meeting slab on grade condition, and it's the transfer of energy at that joint. And that, how do we figure that out if we want to try and reduce the amount of energy used? Katie asked me earlier, have you done that before on a project? And I said, yes, we didn't have to submit anything, but we just wanted to be kind of close to what they were asking. They asked for 10% more envelope performance than code value. And they had no budget, of course. So I was trying to figure out ways that we could get more performance from the envelope by debridging slab and wall. And after looking at it, I figured it was about 2% of building heat loss at this joint that ran all the way around the building for the entire perimeter of the building. We couldn't get full breakage everywhere. We had slabs going across doorways and things like that where it was a constructability, quality, and durability kind of thing. We just kept that, but for a big portion of it, where we had regular walls and stuff, we were able to bring rigid insulation past the thing, and that helped us to get to that 10% over code minimum wall performance, insulation performance. So that is called the psi value, and it is just, instead of being square feet, it's just linear feet. And we'll show you. I can show you how to. Basically, I'm going to try and show you what you do in THERM to do that. There's also point conductivity, which is maybe if you have one steel tube sticking out through a wall to support an awning, and you have 15, 16, 17 of those, then you can calculate that as a point heat loss. This is kind of if you were to try and in THERM and you were looking at wall/slab assembly. This Brian, there we go. This was from Brian, one of your projects. You'll remember a long time ago. Again, just looking at different ways. There were 4 or 5 different tries at seeing how to break that, and just looking at trying to get it so the concrete wasn't touching concrete, touching basically outside air. One of the issues that you can look at here too is surface temperatures, which can be a problem for if you have concrete at a really cold temperature connected. You might have a condensation issue if it's not receiving a proper amount of ventilation and heat. So that's something else that you can look at. We were looking at where the dew point might have been in the building at certain times of year. That's another thing that you can look at. I'm not necessarily going to get into that, really. There's some other fun softwares out there that can do really fancy yearly analysis of. Scott, have you used Woofy? Yeah. Yeah. So they can do a vapor migration analysis along with thermal analysis to see if you're going to potentially have any.
So what is the red line there?
It was the dew point for a specific time of year, and so it was in the middle of this assembly, which was I think it was a fiberglass insulation system. I can't remember. This was 4 years ago. It's been pushed out of my mind. But if your line is before one of your condensing surfaces, then you might have a problem. That means the surface on the other side, which would be that sheathing layer, might be colder than what you would get. But it fluctuates over time. Stuff might get a little bit wet, but if it's not sitting at that like for 3 months, then you're probably, you don't have to worry too much about it. But that's what that Woofy software is for. You can just kind of identify little bits of problems here in this THERM software. So to be able to calculate that psi factor, you'll have a condition, and this is showing a corner condition. Maybe 2 walls meeting. You won't have the same thermal performance as you would at any particular clear wall assembly, so just in and out. So the way that you do this is basically the performance of the detail versus the performance of the same spans of the clear wall assembly, and you subtract the difference to get the total heat flow through that detail component. You look at the 2-dimensional heat flow model. It'll give you the U factor for the detail, and then you've got the lengths of the wall 1 and 2, and then basically come over here and use the clear wall assembly, which can have much better performance, thanks to the 2 assembly U values to arrive at the total, and then subtract the 1-dimensional from the 2-dimensional, and that'll be the total heat flow. So some recommendations on how to do that. And Skylar, you pipe in too, because I know maybe Scott, you too. modeling one of these details, 3 times the thickness of the assembly. So if this wall is 10 inches high, I'm going to model it 30 inches up to get a good sample of, because there's going to be more thermal conduction right at the corner and up here, because that's almost like clear wall assembly by the time you get that far away from the detail.
So if lines are one-dimensional, they're not fluctuating, you've got to clear.
Yeah. Yep. And this was a recommendation from Passive House Academy to use 3 times the width of the material. So if 10 inches inside to outside face, they use 30 inches up. And then whatever this assembly, say this is 12 and 36 inches, you would go from the inside up, out, and the floor to 30 inches up on that one. So, and if you're just dealing with a corner wall assembly, you don't have to deal with anything else, just the 2 components coming together. But if you're doing slab, there's another, I'll have on the next slide, recommendations for how to model the ground interface. Again, just note, so what you're getting is wherever this condition occurs, it's just measured in a linear distance. Once you arrive at the psi value, then you'll have a thermal transmittance number, and you can get how many BTUs by multiplying across the distance and just use a linear footage for that versus U value, which we're normally using for a whole wall clear assembly. For if you have a ground detail to model some of the earth outside the building. So and I think this was also from Passive House Academy. 1 meter from the outside face in, 2.5 meters out. Outside air temperature condition, which I'll show you boundary layers when we walk through some of the therm stuff. This is an indoor boundary layer. And then what it's saying is to do the average of the 2 temperatures for the ground boundary, and that'll run all the way out to the edge of this, and then this ground boundary condition is just adiabatic, so there's no heat transfer happening between that and I just wanted to wrap that because we only really talked about, so that's the method to get to this portion of the equation. If you're going to really get really detailed in figuring out how much energy is going to transfer through your wall, so it's just the sum of the psi value times the total length. And then this is the chi, which is the point transmission. So if you have a tube sticking out of a building anywhere and you have 20 of them, the total is going to be 20 times however many BTUs you're getting flowing through the tube at any given time. And that'll give you your total wall U value assembly if you add in all of the linear and point transmission. So an example, there's that clear wall assembly, steel studs with horizontal girths, and that's, this is where you have a slab intersection coming in, so that's a linear or psi value. And then this is where you have steel tubes sticking out, so it's a point value transmission that you can add into that. Mm-hmm. Oh, sure.
Can you speak to the units on the bridging analysis and what the range of numbers is?
The units on the bridging analysis, what the range means. I think maybe what they're asking is how you're getting to how many BTUs. We can email too. I'm not sure. So this is just kind of an example of what you might have included in if you're doing a total wall analysis. Sorry, it's so low. I forgot how low this one is. But you might want to look at the parapet. You might want to look at the slab intersection, wall transition, and a corner. And those will all get included into the analysis if you're going to do a full analysis to figure out everything. And that might look like this. You're trying to figure this wall out. You have this detail, the parapet detail, the slab intersection detail, and the detail around the windows to try and understand the total wall U value. They're one-offs on assemblies. Never done this. They make you do it. You have to analyze all of your assemblies. But on a commercial,
They are thermal bridge free. You can clearly look at it.
yeah.
It's going to not be a problem. You don't have to
Yep. And then, but on commercial buildings, we're just not required. There's no legal requirement for us to analyze any thermal bridging. We get performance, prescriptive-based requirements in the code or performance. We could probably model the clear wall value, and that's it. That's all we need to do. We're meeting the U values listed there. So this is where you're going to try and go beyond code probably right now. Having read some of the stuff from BC Hydro, I think in British Columbia there's some more specific requirements about thermal bridging, and that's why I think the electric utility sponsored the design guides that Morrison Hershfield has on their website. And they're really good. There's guys over there that do this all day, every day. I do it every once in 2 months. So the guide that they produce will explain everything that I just stumbled through in much greater detail, with all of the methods and calculation methods and everything that that would be required to do this whole building assembly. If you're doing a high-rise, this might be worthwhile. If you're doing one building that's wood stud, it's not going to be as big of a deal.
In Europe, they basically assign default values and have a library you can choose from.
Yeah.
And you basically choose what your details most closely resemble, and you have to use the default values for all of those connections, and then you prove that you're embedded in that. So it's like even in the UK and in Germany, Austria, they are kind of that.
Yeah, yeah, and we don't have anything like that yet. Maybe we'll get there in some period of time. But so that was about 45 minutes, and I was going to hope to just show people the interface. They probably haven't seen it before. So again, it's the material. Take a look at some of that Morrison Hershfield stuff. It's great for commercial building information. Passive House Academy, good for residential building information. Your local building science resource. And then, again, I listed a couple of the BC Hydro is where that thermal design guide stuff was generated and by Morrison Hershfield. They also did that ASHRAE RP 1365. And then windows.lbl.gov software is where you can download THERM for free. And so what I'd like to do is to open THERM and just show a little bit about it. Are there any questions? With the software. So I started it up. Oh no, that's not going to be very good for everybody. I'm way up here. Yes. Okay. So I just loaded in, this is a basic standard wall system, grouted CMU, 32-inch centers, steel stud interior with pretty common old school wall. Basically, when I'm trying to do these, if I'm trying to figure out a Clearfield assembly, I try to give enough space across it to include, for instance, get a few of those grouted cells in there to make sure I'm getting enough of that area to understand what the actual performance is going to be, instead of maybe modeling 1 or 2 blocks. I want to get a few of the blocks with a few of the cells in there and get enough of the studs in the wall system to see what it's going to perform like. So in here, it's really the basics of the program are you're just drawing polygons and rectangles. It's really fussy about getting corners and edges right. So get out of here. See, fussy. So if I was to start drawing a wall system, it's, snapping is important, and it's done with the space bar in this program, but when I'm trying to draw really little detailed stuff, I hit enter and then I type in the distance I want to, and then I hit over. Oops, excuse me. Sorry, these are always great when you do live demos, but so I can type in distance, and usually if I'm trying to draw little tiny steel studs, it sucks, but I've found that trying to draw them, and you can import drawings too. Is that you're going to say? Yeah, you can snap on drawings. Sometimes I've found that they don't snap well to your DXF sometimes.
Usually the is the snap underway, but you can also import it in polylines a little bit, so the geometry will import in and automatically convert into an object, and then you just assign the thermal conductivity properties to it.
Yeah.
I find that if you put the, you set the grid maybe like an 1/8 of an inch, and you make sure that your underlay is aligned with that grid, then everything will snap to some alignment of an 1/8.
That's probably the problem I've been having, is that I haven't snapped the drawing to the grid.
Yeah, to do that, you have to
See?
it's not that hard.
So to those, see, they know better. They know better than I do. I just learned something there. If you draw, you can import a drawing. You can trace over it, line it up to your grid, and basically you can draw your assembly. And what you can do is calculate. I just want to show you some of the outputs really quick, since not many people have seen this yet before. Yeah, I said it's really fussy. If you have little overlaps, it'll say, sorry, figure out what's wrong. And it can be a little bit frustrating, but yeah, if you use the snaps and you trace the drawings, it's usually a little bit better. Just kind of some time invested in the beginning is good. But one of the other things that I probably ought to show real quick.
So basically what you do is draw with rectangles, and then we'll do kind of objects that you can click on and then find a material.
Yeah, so let's, I've got the architectural library loaded up. So I just clicked on, this is a piece of that CMU block, and you can see how I kind of split them up. And it's not totally exactly like a CMU block would look, but it's got the close amount of area, yeah. And then I just loaded the architectural software, and then we can change this to any number of materials that are with preloaded values. If you have a value, if you have a specific product that has a different type of value, you can modify this pretty easily. Yeah. Yeah, if you get materials figured out and save them in your library, then it starts getting easier. And there's a good selection of, I mean, these are just, if you're just starting off, I think most everything that you'll need typical will be in here. You've got different weight concretes, you've got steel, you've got wood, you've got different foam insulations, fiberglass, particle board, gypboard, pretty much everything you need. So basically what we'd have to do is recalculate now that I have the, I don't know what I put on there, rock wool, something like that. This is one of the outputs that you can see, which is basically giving you lines of temperature difference. So if we have our interior condition is a typical 68 degree with temperature, and the exterior degree is set to, I think I actually put in a, so they're designed or Pocatello or whatnot, and so it's just the design temperature for, and then, let me see here. The other thing that you can pull up really quick is basically this is what you would need to get that performance value for the code.
You probably want to switch to units though, because that's for
Oh yeah. Oh, sure. Yeah, Skylar was just mentioning to switch the units because, again, we have the foot thick unit here. Let's see. There's a few other things that you can look at. Flux vector shows you kind of where all of your transmission is happening, and that's obvious. It's at the steel studs in this one. Transfer is happening. I think it took to be able to draw a wall system.
A little while
Like a day or two.
to actually import the drawing.
If you have a detail that you want to test, you've got it drawn obviously, and then you just getting it in here and learning is probably a day or two.
Yeah, I mean, that's around it at that time. I couldn't get it.
Yeah.
Another thing is when you get into multiple temperature boundaries, like if you're trying to do a ground connection and you have like an intermediate boundary in between there that's semi-conditioned, and then you have, so like if you have multiple interfaces, like a leftover non-conditioned basement and partly conditioned crawl, and then have a slab detail, and then part of it's slab edge below grade, like a certain depth, and part of it's above grade. It just can get really difficult to manage all of that.
And then, as far as practice goes, the way I've used this so far is retrofits and figuring out what I can do to get enough insulation to work with what furring, and that's what I've used. I mean, 3 different jobs. That's what I've used it for. One new construction where I looked at the psi value around the whole perimeter of the first floor, and that's so far that's what I've used it for in practice sense. I haven't done whole buildings like passive house is required, but just here and there when needed. Figure out wall system U values through a spreadsheet method if you just have a different stack of materials and it's consistent. But that's all I had.
I have a couple
I'd be happy to
things.
play around with this a little bit more with anybody that wants to afterwards.
I have a couple things from online. They would like a summary of the suggestions that the audience member gave for how to import the geometry, and then any good pointers on getting DXF files to be imported, AutoCAD release, use of polygons, verse lines, etc. would be helpful. So
Yeah,
basically, drawing the geometry.
Yeah, I think it's if you export the objects from AutoCAD as like if they're all closed polygons, then or polylines.
Yeah.
Then
Right.
then when you import it, if you go up to File, right there, and you do it at Import
Oh, let me drag
or
this
Underlay
down a little
actually.
bit here.
Sorry. Go File,
Yep.
Underlay, and then you can select Auto Convert there on the left when you import your DXF file, and then it should underlay. And if the polylines are done properly, then if they're all closed polylines, polygons at that point, then it will convert them into shapes, and then you just assign the material conductivities to each shape. You don't have to really draw anything. Otherwise, you just do it. You can underlay the DXF file, and then you just trace it, like Gunnar was saying.
Yeah, tracing's pretty tough, and when you draw, and everything has to be closed polyline, because otherwise there's it'll have errors, and sometimes if they're tiny little things that you're drawing, then they'll be really hard to find.
So another good drawing method too is if you have a complex shape, you'd make a die for it, you make shapes around it, and then you fill it with paint with the paint bucket.
Yeah,
so that
I can show that real quick too. Turn that off. So, for instance, this is actually one of those. And what I did before, I think, was to fill it, I just drew something here, and then I can paint bucket that.
And then if you hit the eyedropper button, you can, of course, copy the material and paste it in multiple locations, so you don't have to keep selecting it from a menu. So that's helpful too.
Yeah, so I can change my CMU back to CMU.
And then if you hit that little button, if you're going to be drawing a bunch of polylines, see the button to the right of the rectangle button that has like the multiple boxes?
Oh yeah, there we
Then
go.
it repeats your tool and you don't have to continue to go up to the menu and reselect it. So that's a really helpful trick as well.
Yeah, rectangle, polyline, so you can draw complex shapes, measuring tool.
It's important to check your scale if you do the underlay.
Boundary conditions, so those are, you have to identify where the outside air is, basically. Is this outside temperature? You got one where you got to identify the inside temperature layer. And then, like Skylar was saying, if you have multiple boundary conditions, then it gets kind of tough. You have different temperatures in different areas, all those kinds of things. Sure. So it'll find boundary conditions too. So this is what I usually do because my walls are really simple. Skylar, if you have a drawing method too, but usually that's what I've done, and then I just use that BC, and then I select what I can find. So these are all adiabatic because it's just continued more wall on that end going forever, and same thing on the other side. And then this one is changed to an outside boundary layer, and this one is an interior boundary layer. So usually it's once you get your drawing done, if everything works, you can use this BC. That's where a lot of times you'll find out, something isn't closed or something overlaps. It'll tell you have errors. If I have errors, I usually try not wholesale go through but just take one thing off at a time and save as until I find it.
That's the key. It doesn't have auto-save. So, like, I've drawn shapes like this before. Like, you can draw shapes like this, and then you go to calc it, and then it freezes during the calculation, and you lose all of your work. And so you have to, before you like hit boundary condition or calc, it's critical to save every time. Because it's, like if there's overlapping geometry, it can freeze, and then you lose everything.
Okay, I'll try.
The first one is, are the numerical solutions verified versus field data by the developers?
By Lawrence Berkeley Lab? Yeah, I think that the development of the tool is based on hotbox tests, maybe with Oak Ridge.
Okay.
I'm not sure though. THERM's been around for, good God, I don't know, 20 years, 30 years.
Okay. Another question.
But it is the standard for NFRC ratings to do window modeling using Windows 6 or 7 or whatever it is now. So the national rating system for fenestration uses THERM to do the modeling to.
And we might have to follow up with some of these afterwards, so I might leave it at that. I know people need to go. They can take off, but thank you to Gunnar, and then also thank you to Idaho Power. They sponsor this series for